This is a video dealing with section 3.4, which is going to be all about graphing polynomials. So what I want to point your attention to at the very start is the first three graphs. Now take a look at all three of those. Look at the equations and ask yourself, what kind of a degree does each one of those equations have? And you'll notice that each one of them is an odd degree. Now take a look at the graphs. Not the equations, but the graphs, and ask yourself what's true about the symmetry. This was back, we covered this material for the last test. What kind of symmetry do we have? Well, each of them has origin symmetry. And remember that origin symmetry also means that I have an odd function. When we take a look at the domain and range is all real numbers for all three of those graphs. And also notice that each of those graphs is increasing from left to right. And one way that I like the way that the author notes this is that it looks like they fall to the left and rise to the right. Now look at the next three graphs. You'll notice that all three graphs have symmetry with respect to the y-axis. The equations of all three graphs, you'll notice that the degree is even. And if I have symmetry with respect to the y-axis, you remember that that is going to be an even function. The domains are all going to be from negative infinity to positive infinity. However, the ranges are all going to be from 0 to infinity. And they are continuous. If you'll look at increasing and decreasing, all three of these will be decreasing from negative infinity to 0, but then they will be increasing from 0 to infinity. They both rise on the right and the left sides. Now, this next box that's in your notes, all of this is a review from section 2.7. So honestly, I'm actually not going to cover this with you. All of this is straight out of 2.7. You can go back to your 2.7 notes or you can pause right here, but all of this is from section 2.7. It's just dealing with our translations, and so that is a review. Let's take a look at example number 1. Example number 1 says that, first of all, we should graph. Okay, so when you ask yourself what's happening, this is my cubing parent. I'm adding 1 to that, so we know that this guy is going to move up 1 unit. So my cubing parent, you can see that I've got the coordinates there marked out. The cubing parent starts at the origin, starts at 0, 0, but I shifted that up 1. From the origin, it goes right 1, up 1, and right 2, up 8. And then it goes left 1, down 1, and left 2, down 8. And then I'm also supposed to tell about increasing and decreasing, and this guy is increasing over the entire domain. For the second one, you'll notice that we have this parent that is raised to the 5th power, and that's not a parent that we've ever worked with before. But if you'll take a look, you actually were given x to the 5th, the parent, just a few moments ago. So it looks a whole lot like the x cubed parent. And so what we have here is that I'm taking my x to the 5th parent and I'm going to shift it to the right 2 units. And basically what we have here is it's going to go right 1 and up 1 and down 1 and left 1. I could say that I was going to go to the right 2, but I would need to be able to go all the way up to 2 to the 5th power, which is 32, so I just don't have enough blocks for that. All right, and then my increasing and decreasing for that guy, it's always increasing over the whole domain. Now if we'll take a look at this one, we also have not done an x to the 4th parent, but we know enough about translations to know what we need to do. So the first thing that's going to happen is it's going to move to the left 3. And then it's going to be reflected over the x-axis because of that negative. The 1/2 is going to cause a vertical shrink. And last but not least, the plus 5 is going to cause up 5. And if you'll notice, I gave you an x to the 4th parent a few moments ago. It looks a whole lot like the quadratic parent. It just looks like it's a little flatter, kind of like the quadratic has been dropped onto the x-axis. So that's essentially what we're going to do as we graph this one. Just going to make it just slightly flatter. And you'll notice that I went right and left 1 down a half because the parent would have gone right 1 down 1. And so that vertical shrink by a half is what caused that. Left 3, up 5, and then the reflection. All right, so unless otherwise restricted, the domain is simply going to be the set of all real numbers. That is the symbol there for all real numbers. And they're going to be smooth, continuous curves over the whole entire domain, which is going to be from negative infinity to positive infinity. The range, and by the way, that is for an odd degree. The range of the odd degree, sorry, is going to be all real numbers. But if I have an even degree polynomial, its range is going to be either k to infinity or negative infinity to k because of the fact that it's going to turn around, much like the quadratic does, and even this one here. And you know what? Now that we're talking about the domain, I was supposed to give increasing and decreasing. So let's go ahead and do that really quickly. So the first thing that's happening is it's increasing from negative infinity up to negative 3. And then it turns around and it starts decreasing from negative 3 to positive infinity. And just remember that increasing, decreasing, and constant will never, ever, ever, ever use square brackets. And they'll always use the x values. All right, let's talk about the behavior around the x-axis. So you have 3 different examples given to you here. The first example that we are looking at, notice that my 0, my x-intercept, the behavior around that x-intercept, it's going right through the x-axis. Whereas on the second one, I'm not going through the x-axis, I'm bouncing off of the x-axis. So I like to call this middle one a bouncer because they're bouncing off of the x-axis, whereas this first one I call it a breaker because it's breaking through the x-axis. If you'll take a look at the third example, I'm breaking through the x-axis, but it's a very slow breaking through the x-axis. And notice that what causes these breakers or these bouncers is the multiplicities of my zeros. So we talked about multiplicities in section 3.3. That was the first time we've been introduced to it. So when I have a multiplicity of 1, it's going to break straight through the x-axis. If I have an even multiplicity, so something that is squared or something that is to the 4th power, these are going to be bouncers. They're going to bounce off of the x-axis. If I have an odd multiplicity that's greater than 1, so a multiplicity of 3 or 5, then this is going to be, it's still going to break through. It's just going to break through slowly. So this is how I'll know what kind of behavior I have around my x-intercepts. Now, for the next section, I've drawn 3 different examples here. One of them is a common quadratic, one is a common cubic, and one is a common quartic. And I want to take a look here at the turning points of each one. So you'll notice with this first one, my degree, as you know, is 2. Here, my degree is 3, and a quartic has a degree of 4. And these are things that we've talked about before. But look at the number of turning points. This guy only turns around once. This guy turns around twice. This guy turns around 3 times. So what's the pattern then? The pattern is that the number of turning points on my graph is always going to be 1 less than the degree. 1 less than the degree. All right, now let's talk about the end behavior. All right. Now this box is pretty extensive, so we'll go through it fairly slowly. But let's take a look at what we're dealing with. The first thing is that I'm looking at a polynomial, ax to the nth power. And this is, notice it calls it the dominating term. And I have said the leading term. And so this is going to be the term where the degree occurs. Notice that for this first one, this first set, I have an odd degree, whereas when I get down here, these guys all have even degrees. So the first set has odd degrees, the second set has even degrees. Now, if my A value is positive, so that's the first choice. If my A value is positive, the end behavior is going to look something like this. This is a lot like the very first three examples that I gave you. I've made the middle of the graph dashed simply because I don't know how many wiggles are in the middle. This is called end behavior, so I'm only working on what's happening out on the ends. Now, you'll notice I've got several different notations here for you. This first one talks about when my x approaches, that arrow says I'm going towards, or I am approaching infinity. Well, we know that x approaching infinity, this is going towards the right. And so as I look at my end behavior over here, as x is going towards the right, y is going up. And so we'll say then, since y is going up, y is going towards positive infinity. As x goes towards or approaches negative infinity. So this is going to be on the left side over here. As x approaches negative infinity, the left side, my y's are going down. Well, how do I write that? My y's are approaching negative infinity. Well, then what we have is, the next part of this is when my A is negative. And when my leading coefficient is negative, then things start to turn around. So my end behavior, first of all, is going to be different. So this time, as x approaches infinity, again, x approaching infinity is on the right-hand side. So as x approaches infinity, that's on the right. What are my y's doing on the right-hand side? Well, my y's are going down. How do I write that? Y is approaching negative infinity. And then secondly, as my x's are going towards negative infinity, well, that's this side of the graph. And so we'll say that our x's are going to the left. What are our y's doing as x is going to the left? Well, my y's are going up to positive infinity. All right, so let's do the same thing then if our polynomial is an even degree. Well, first of all, if polynomial is going to be an even degree, we know because of our dealings with quadratics, either both ends are going to be up or both ends are going to be down. And we also know that the leading term, the sign of the leading term, is what determines that. So let's first of all look at when my leading coefficient, is positive. We know that that's going to be both ends are up. So once again, as x is approaching infinity, so x is going towards the right, what is y doing? Well, y is going up. So we have x's are going towards the right, y is going up. What does that look like? Y is approaching positive infinity. On this other one, x's are going towards negative infinity. Well, as x goes towards negative infinity, which is the left, what are y's doing? Well, y's are still going up. So as x goes to the left, y is going up. So it's going to be y is approaching, again, positive infinity. Well, now let's look at when my leading coefficient is negative. We know that that's going to turn our quadratic upside down. It's going to turn every graph upside down. And so when our leading coefficient is negative, let's look at when x is approaching positive infinity. This is the right side. Notice that my y's are going down. So as x is going to the right, y's are going down. We write that as y approaches negative infinity. And then last, if my x's are going towards negative infinity, so this is on the left side, my y's are going down. And we would write that as y is approaching negative infinity. All right, so now let's put this into practice. What is the end behavior of each of the following? So you'll notice here that for part A, my degree is 4. So this is either going to be this guy or this guy. But I have a negative leading coefficient. So since my leading coefficient is negative, both ends will be down. For part B, I have a leading coefficient that is positive, and I have a degree that is odd. So it's going to be overall uphill. For part C, again, I have a degree that's odd, but this time my leading coefficient is negative. So it's going to turn around and it's going to be overall decreasing. And then lastly, part D, my leading coefficient is positive. My degree is even. So both ends are going to be up. So then how does the term of the greatest degree, or the leading term, how does it determine the end behavior? And so there's two things that you have to look at. First thing is you want to ask yourself, is my degree even or odd? That'll determine whether both ends are going up or down, or it'll determine whether both ends, one is going up and one is going down. So first question, is your degree even or odd? Second question, your leading coefficient, is it going to be positive or is it going to be negative? This is going to determine the end behavior of your polynomial.